over the objectives, setup, results, conclusions, and references. Some of the objectives of this experiment were to perform a free vibration experimental measurement of the cantilever beam, use a strain gauge to specifically measure dynamic tip displacement, measure dynamic beam displacement from comparison to theory, and perform analysis of time-dependent tip displacement to determine the natural frequency of a cantilever beam. First, the experimental setup included creating a Wheatstone quarter bridge strain gauge, as shown in this figure. Then next, we set up a cantilever beam by clamping one end of the ruler with a strain gauge attached to a cardboard plate as the reference plane and to a table to create a rigid boundary condition, as shown in the figure. Static measurements, static strain gauge sensitivity. The purpose of this task was to find the sensitivity of the strain gauge. The data was obtained by placing various loads of the tip of the cantilever beam by measuring the displacement of the tip in reference to the reference plane. There's a linearly increasing correlation between the tip displacement and the average voltage output. The strain gauge sensitivity was determined by creating a polynomial fit for the data and finding the slope of this fit to show the linear plot. There's a slope of 18.0136 times 10 to the negative 3 millimeters per volt, which is the estimated sensitivity. Assumptions include a fully rigid boundary condition and load placed at the exact tip. And these results show that there's a clear linear relationship between the tip and the strain gauge voltage, confirming that the strain gauge sensitivity is accurately estimated using the slope of this polyfit. To find the equivalent stiffness of the beam, we found first we need to find the equivalent stiffness of the beam, and there's a linear behavior in this beam. So the stiffness was found by using a polyfit to get a slope of the data of the applied load and the tip displacement, and we found that the slope was 20.2848 times 10 to the negative 3 newtons per millimeter. And assumptions included fully rigid boundary conditions and load placed at the exact tip. Dynamic measurements, initial displacement, excitation. First, we slowly displaced the beam's end by 15 to 20 millimeters in reference to the cardboard reference plane. Then start the DAC in the MSP 432 GUI and wait 1 to 2 seconds, then fully release the beam to allow free vibrations. Save the data and repeat for a total of 3 trials. For the first few seconds, there is constant displacement of around 20 millimeters, and after the beam is let go, and the beam goes into free vibration. As the time goes on, the beam goes into steady state oscillation. Initial displacement excitation. To estimate the damped natural frequency, use the following formula, and TD is the period of oscillation. And using these two formulas below, you were able to get the damping ratio. And finally, we're able to get the natural frequency with the following formula at the bottom. So some of the system's parameters estimation included, since the damping ratio is less than 1, the system is underdamped. Also, physically, when a system is underdamped, oscillations occur, and there were oscillations present physically during the experiment. And these were some of the results that we attained in case 1. Initial displacement excitation, experimental versus theoretical. Below are is the equation of motion, and these are the following variables that are included in this calculation. And the theoretical value does not seem to actually be extremely accurate compared to the measurements below. When doing spectral analysis, you pick a specific window to analyze the spectrum and use FFT and then normalize the number of samples. And there were 2 peaks found in this part. And the natural frequencies are negative 40 hertz, and while we found that earlier that it was approximately negative 10 hertz. With the same setup, a quarter was dropped after an initial drop. This was the longest one to reach steady state due to a high impulse, as shown in the picture. Pick a specific window to analyze the spectrum as before, and there was only one peak present. And this was also lower as it was -50, and but we found it earlier as -10 Hertz. For vi viscoelastic dampening, we use two types of tape, duct and carpet tape. Through the experiment, we found that the dampening ratios of the carpet tape was the highest and no tape was the lowest. These are all the measurements of all of the tapes found above and all the cases that we had measured. One conclusion that we came to, or I came to, was that the carpet tape was a better dampener than the duct tape as it provides higher damping ratio and lower natural frequencies. And the damping ratio goes up as the natural, and the damping frequencies decrease, showing an inverse correlation between the two. And these are references. Thank you.